So thank you everyone for being here. Actually, so today we have the great pleasure to have among us Dr. Jonny Rutqvist. Dr. Rutqvist is a senior scientist and head of the hydrogeology department in the Energy Geosciences division at the Lawrence Berkeley National Laboratory. Dr. Rutqvist holds a PhD degree in engineering geology from the Royal Institute of Technology in Sweden. And for over 30 years, he has been working in the field of geomechanics with a particular focus on computational modeling of coupled multiphysical processes, including in particular thermal, hydraulic, mechanical, and chemical processes, with respect to geological media for a wide range of scientific and engineering applications. The problem that Dr. Rutqvist addresses with his team are many, and they include geologic carbon sequestration, nuclear waste disposal, geothermal energy extraction, unconventional oil and gas, as well as underground energy storage. Dr. Rutqvist has authored over 200 peer-reviewed journal papers, and he is a 4-time recipient of the American Rock Mechanics Association Awards. Today, actually, he will inspire us with a talk entitled Coupled Processes Modeling in Energy Geosciences. And he will actually talk about 3 major projects, geo-energy projects on which he worked and on which he published seminal contributions, namely the nuclear waste repository at the Yucca Mountain in Nevada, the In Salah CO2 storage project in Algeria, as well as the Northwest Geyser enhanced geothermal system in California. That being said, thank you again for being among us, Jonny, and I leave you the floor or maybe the screen.
Oh, thank you.
Thank you.
I will share the screen.
Perfect.
So, thank you for the kind introduction. Yes, so as you heard, today I will talk about coupled processes in energy sciences. So I will present some examples from the work we have done at the LBNL, such in the past, on the modeling of large-scale field data for modeling of kind of a model validation and understanding of coupled processes in the field. And here is an overview of different geoenergy activities, energy geoscience activities. So that includes, for example, you have a carbon sequestration, nuclear waste disposal, energy storage, so where we dispose waste and store energy in the earth, and other types of energy geoscience activities, including hydrocarbon, geothermal energy extraction, so where we extract oil and gas and heat from the earth. So in all these activities, a good understanding of coupled processes, I think, is crucial for assessing the performance of such a system. And this is what I'm talking about if I'm talking about coupled thermo-hydromechanical processes. So you can think that you can have temperature changes, you can have changes in fluid pressure, you can changes in mechanical processes, and then there are couplings between those. So if you go from thermal processes to mechanical on top, there is thermal expansion of the material, and that would induce stress and strain changes into the material. Or if you go on the bottom between T and H, so you can have changes in fluid density and fluid viscosity and thermal heat convection. You can actually cause kind of heat convection cells in the porous media. Or if you go from hydraulic to mechanics, you can have changes in the effective stress that induce mechanical stress and stress changes that in turn can change the porosity and permeability. So you change the fluid flow properties. So all these processes are coupled. And in the energy geosciences, so changes in permeability, for example, in the fracture media, could be important to change the permeability. So to model these phenomena, I actually used a model which are called TOUGH-FLAC. So this is a numerical simulator for coupled multi-phase flow, heat and transport, and geomechanics. And it's actually based on linking our multi-phase flow simulator at the Berkeley lab, TOUGH, with a FLAC 3D geomechanical simulator. And this was actually first developed in the early 2000 when for analyzing coupled THM processes in the nuclear waste program at Yucca Mountain. And one of the reasons was that TOUGH was already used in that project, and then I had to link it. TOUGH cannot do mechanics, so I had to. They were interested in the effects on mechanics on the system, so I had to link the TOUGH to another simulator, and finally chose FLAC 3D because that one was already qualified in the program. So there were a lot of thinking about quality assurance. So these two simulators are sequentially coupled. So you have what I call direct couplings, solid red lines, including pore volume changes, effective stress and thermal strain and swelling. And then what I call indirect couplings, which are changes in mechanical and hydraulic properties. For example, if you have a stress changes, those may change the hydraulic properties, permeability, porosity, and maybe capillary pressure. If you have unsaturated media, which goes into the flow equation. So this is a simulator. I mean, there are many other simulators that maybe could be used as well, but this is one I have been using, which I find quite useful because you have many fluid equational states and constituted models available. So it's relatively easy to expand to different kinds of application areas. So today I'm going to talk about 3 different examples of large-scale field data systems involving 3 different energy geoscience fields: nuclear waste disposal, geothermal, and CO2 sequestration. So in the case of nuclear waste disposal, you see here, I will present the results from the modeling of large-scale field heating experiment. In fact, it's the largest in the world underground heating experiment conducted at the Yucca Mountain site in Nevada, and involving thermally driven, strongly coupled multi-phase fluid flow and geomechanics processes in a fractured media with fracture matrix interaction. So change in permeability is relevant for nuclear waste disposal and contaminant transport. Then the second case will be the results from the Geysers geothermal field in California, which is the largest geothermal energy producer in the world. So this involves injecting cooled water into very hot fractured reservoir, leading to strongly coupled multi-phase flow and geomechanics, and induced seismicity and permeability changes, which will impact the geothermal production. And finally, in the case of CO2 sequestration, so we show results from the In Salah CO2 storage project in Algeria that involved millions of tons of CO2 injected at relatively high pressure, with some very significant geomechanical response in the caprock, which you will see, and induced seismicity is an issue in all of these applications. So if we first go to nuclear waste disposal, so this is actually showing the design of the then proposed nuclear waste repository at which was supposed to be located in Nevada, state of Nevada test site. And to the right, you see the general design. So the repository was going to be located at 300 meters depth in the unsaturated zone. So this is very dry area, is in the desert, and very low rate of infiltration from rain. So it's unsaturated media at 300 meters depth, and then the water table is located at 300 meters below that, so at 600 meters depth. The host rock is a welded tuff, fractured tuff. It's a hard fractured rock, and quite permeable actually. And the design was down to the right. You see the design. Can you see my mouse on the screen?
Yes, we can.
Okay, yeah. So here you can see so they're going to place the large waste canisters into open tunnels. Those are tunnels of about 5 meters in diameter. and they are open, they are not backfilled. And then the groundwater flow may flow from the ground, very low infiltration, but then there should be a capillary barrier to divert the flow around the tunnels. So that was the design, but they also included some engineering measures that they put in like a drift shield here to protect for that. So they don't want to have fluid seeping in they want to avoid corrosion of the waste package. So in this system, you have strongly coupled THM processes, and occurring during the early time where you have where the waste is hot. And when I say early time here, I mean maybe the first few thousand years. So you have a temperature up to 150 degrees in the tunnel and in the near host rock. So you have number one, you have heating of the rock above boiling temperature. You have the formation, also the dry out zone, because you have a vapor and vapor flow advection in the fracture system. At the same time, you have a re-wetting of liquid, actually mostly in the matrix rock, because the matrix rock has higher saturation than the fracture system. There are thermally stress and deformations induced and THM induced permeability changes. And then the question is, how will that impact the long-term behavior of the system? So, it's going to be for 10,000 years or even more. So, what is the impact and stability of the drift opening? Impact on the capillary barrier function? Impact on the excavation disturbed zone? We have changes in permeability and changes in potential changes in transport properties. So this is something we should investigate to the THM model, and then that will be handed over to people doing radionuclide transport modeling for the performance or safety assessment of the repository. So the Yucca Mountain Drift Scale test was done to simulate this kind of a repository tunnel. And so here you have actually heating up to 200 degrees. And it was conducted in this exploratory studies facility, which actually a tunnel going into the host rock for characterizing the host rock is at the site. And so this experiment, so you have those heaters. Here is a heater inside the tunnel. And there is also what they call wing heaters, and these wing heaters were to simulate the effect in a repository. You would have neighboring tunnels as well that would impact the heat load on the system. So there's a 4 years heating followed by 4 years cooling, temperature up to 200 degrees near the drift wall, and measurements of THM change, CHMC changes in several hundred sensors in these boreholes you see here. These include temperature, hydrology, I will talk about mechanics, so the extensometers, and this is ERT, is electric resistivity tomography. Of interest for me especially was these experiments that is evaluating the permeability of the host rock. So evolution of the fracture permeability in the host rock as a function of time. And as I said, the system is unsaturated or partially saturated. So you have a fracture system where the fractures are initially quite dry, although there is more liquid saturation in the matrix blocks in between. So in this test, they have air injection tests conducted every 3 months. Those are packed off section 3 to 5 meters long. So by this, you can evaluate the evolution of fracture permeability during the heating and cooling of the rock mass. So that air permeability is impacted by both the liquid saturation in the system and also by the changes in fracture permeability by thermomechanical changes. So to model the system, so we use a continuum model, we use a dual permeability medium for matrix and fracture continuum. And that was something that was previously used for the modeling of the flow and transport in the media, this kind of dual permeability model. And then I link it to mechanics. So especially looking at the permeability changes. And at the site, there were 3 orthogonal fracture sets that we included in the model. And then we look at the stress permeability relationship based on changes in aperture of those fractures. So normal stress versus aperture, a non-linear relationship. And we have to determine these parameters. So the residual aperture, and these to see how much they change with the change in effective normal stress. We calibrated those against field data, and one of the field data is this the drift scale test. So here you can see the evolution of the power up to 180 kilowatts, so very high heat power, and temperatures up to 200 degrees. So you go over boiling temperature here, and then up to 200 degrees at the drift wall, and then there's a cooling for another 4 years. So this is simulation results for the temperature. So to the left here, you can see contours at 1 year. You can see you have a above boiling temperature here close to the tunnel and the wing heaters. Here you can see a comparison between the measured and calculated. So measured are at 1, 4, and 8 years. So here you have 1 year, and then you heat. This is end of heating, 4 years, and then at the end of the cooling, it's 8 years. It's still not going back to ambient temperature in the rock, but you can see the agreement between the calculations and the measurements are good. And generally in this kind of system, general temperature, we can usually simulate, predict quite well when we do this kind of heater experiments for, although this is kind of a complex TH process in here, still the heat conduction is dominant, although you can see some kinks in the curves here at around the boiling temperature. So anyway, this kind of temperature induces strongly coupled thermomechanical and thermohydrologic processes. So if you look at the thermomechanical processes, so here you have a hot heat, and so this increases the compressive stresses in this area, which will close fractures, tend to close fractures to lower permeability in this area. There is also some reduction up here, which you can see in horizontal stress. If you look at the TH process, thermohydrological processes, so you can see that here, because of the high temperature, we actually cause a dry out of the fracture system here in this fracture, also in matrix rock. The dry out zone. So initial the saturation was about in the fracture system is about 10%. It's much higher in the matrix, but in the fracture system it was 10%. And then you heat it up, you get evaporation and heat, and the moisture is driven out by the vapor flow or by advection with the gas. And then further out is condensed again where the temperature is lower. So then you cause a liquid zone here moving outwards, and the liquid is then also moving down by gravity. Yeah, so this is liquid flow moving there. So these are those. And then as I said, these changes in wetting in the fracture system and also the stress changes will cause changes in air permeability. So if you start down here, you have a low stress and dry system. This is kind of the initial, relatively higher permeability. And then as you wet the system and you get high thermal stress, you close the fracture and you reduce the air permeability significantly. So this occurs simultaneously. And here we can see one again, the same figure of the thermal stress and the liquid saturation. And then you can see here how we calculate the changes in permeability, change factor. So this is current permeability at 1 year or the initial permeability. So here you have a permeability reduction to almost down to 10% of the original. in this area. So you have the effect of thermomechanical fracture closure, and then there is additional effect of the liquid saturation in the fracture system here. So here you have the lowest permeability, air permeability. We will then look at the field measurements in this point, in this packed off section here, how it evolves with time. So you would see a change, a reduction, but both due to thermomechanical and due to this liquid front that is passing through this borehole. And this you can see here. So this one shows the permeability change factor as a function of time over 8 years, starting from beginning at 1. And here you can see the field measurements. These are measured every 3 months. The solid line then is the calculated with thermomechanical effects only. And get down to this. And then you see the additional effect. The dashed line is the Tm plus Th. So you have this added reduction in air permeability going down here to less than 10%. And then when the wetting front passes, you go up again and coming back to here. Here you can follow that in this figure. You're starting at this point. Dry and low stress, you increase the stress due to thermomechanical changes, and also increase the saturation, you get the reduction in permeability, and then the wetting front passes, you get the dry fractures, but still hot rock. So still fractures are closed by the mechanical changes. So anyway, so after having done that, we also looked at the mechanical displacement and so on to compare to the modeling data. And so you get the model that kind of validated for that system. And then we did some simulation where we applied a real heat decay function from a repository and looked at the long-term evolution over thousands of years. And what we then find that actually not so much impact on, no significant impact on the drift seepage, because it's an unsaturated system. So even if you close or open fractures, it kind of compensates itself and just flow around. And the permeability changes in the host rock, you saw there were kind of within 1 order of magnitude for these kind of processes. We measured that at the site. So that was kind of an input to the further on for the performance assessment models that are done by other people. Anyway, you can find more information in these publications down here. And I'm going to go to the next item is the geothermal, the Geysers. And so the Geysers is actually the world's biggest energy geothermal producer. It's located in Northern California, north of San Francisco, and it currently produces about 850 megawatts. So this is actually a hot vapor-dominated system. So it's mostly steam down there. It's very hot. And isolated by some impermeable boundaries of faults and caprock. So when they produce vapor, the pressure actually goes down. So they need to actually replenish that by water injection. And they do water injection from steam condensate, and they also take treated wastewater from nearby communities. And inject. And this kind of water injection then also actually causes seismicity in the system, which is concerned to the local community. So what I've been working on is actually a demonstration project for enhanced geothermal systems in this area. This was funded by the U.S. Department of Energy. And the idea was, so in this area, this is in the northwestern Geysers, they had drilled exploratory wells in the 1980s and tried to produce, but actually they abandoned those wells because they had problems with corrosion and non-condensable gases. So those were abandoned, but now they have later have been seen that if they inject continuously, they can reduce those corrosive gases and non-condensable gases. So that's the idea of this EGS, is actually to deepen those wells into a very high temperature zone that was discovered in the area. So you can see at the bottom of one of the wells there, they deepened that up to 400 degrees C, so very hot temperature. And so the idea is to have a continuous water injection, to lower those non-condensable gases, and to stimulate the rock fractures and enhance the permeability and enhanced steam production. So you would inject into that blue well and produce steam in the red well. And so that this high temperature zone is also a zone which the permeability is a little bit lower. So then the continuous cold water injection would also tend to stimulate fractures in that and enhance permeability. And this is showing the injection and seismicity at this EGS well for the 1 year of injection. So if they look at the evolution of induced seismicity in 5 by 5 by 5 kilometer cube. So if you look down to here to the bottom, you can see a graph. So this shows in blue curve is the injection rate as a function of time. So this is injection rate over 1 year, starting at 400 gallons per minute. This is the scale here, up to 1,000 gallons, and then lower again. And then each dot here, it represents one seismic event. So here you can see the magnitude of the event. So they go from, so this is the kind of the lower detection limit by the system. So there are many earthquakes smaller than this magnitude, but they cannot be detected. And then up to about magnitude 3. So some of these events, maybe magnitude 3, maybe could be felt on the ground surface. But anyway, you can see before the injection, there is no seismicity in this area, in this cube. But as soon as you start injection, you get a number of events, and you got up to several thousand. Actually, it was 1,700 events during this 1 year injection in this area. So to model this, we again used this linked TOUGH-FLAC 3D simulator. And then we simulate the changes. So these are liquid water injection into a steam reservoir. So this we simulate with PAF, and then we have the temperature and pressure changes and calculate the changes in stress due to this cold water injection. And then we calculate the potential for induced seismicity, consider rock frictional failure. So we actually just simulated the stress changes, and then kind of a post-processing, looking at the potential for induced, for shear of a fracture. We're assuming that the fracture could be ubiquitous of any orientation. And we assume that the kind of host rock is very, very close to near critical stress for shear instability. Actually, this is also what they observed at the site. You just need to inject very little to actually cause small stress changes that could cause some microseismicity in this area. So we want to look at the impact of THM on seismicity and permeability enhancement, and also the sustainability of such a system over the longer term with the modeling. This is the first initial modeling we developed, a kind of a layer cake model where we include the important units. So you have the caprock. You need a caprock here to actually have this kind of steam reservoir. And the NTR is called the normal temperature reservoir. This is a 240 degree. This is a steam reservoir. And then you go below that, you get the higher temperature up to over 300 degrees, and there the permeability is also smaller. So we look at the injection and pressure and temperature and the estimated EGS extent here. So what you see that you actually here there is an injection, but they don't need to inject pump water down. They just need to pour water down actually, because the system is at a very low, quite low pressure. So it's a few megapascal initial pressure in this steam system. So they just need to pour water actually into the system, but they pour it at the rate of up to 1,000 gallons per minute. And then you get the liquid flow going into the steam reservoir. So you can see here there is a cooling near the well, and this is where you have the actual liquid water flow zone going down from the injection well. So this is a very strong couple thermomechanical changes in this area, but it's very limited close to the injection well. And then you see these pressure changes. So these are changes in steam, in the steam reservoir pressure, extending quite far out, but they are quite small changes. So you have up to this area, there is about 1 megapascal pressure change. And that is enough to actually cause induced seismicity, the activation of fractures and induced seismicity. So this is the extent estimated using that simple Moore-Coulomb criteria based on the calculated stress changes. So about one kilometer, and then we compare that to the actual monitoring. You can see that roughly have that kind of extent. And so we did this. This was actually a model prediction, but we had calibrated our model against the nearby injection wells that was ongoing at the time. So this was our initial model. Then later we looked more carefully at the evolution of induced seismicity. So these are the two wells. We are now looking from a map view from the top, 2 by 2 kilometers, and these are the well at the ground surface. So going down. So this is the injection well going down, and this is what would be later would be the production well. These are what they call steam entries. So these are big fractures or fracture zones intersecting the wells where they can pump a lot of steam. Although there are fractures also in between, but maybe it's smaller. So what you can see after they change the injection rate, you can see the evolution of induced seismicity propagating along discrete features here. And this is interpreted as faults or fractures, so permeable faults or fractures. You also have to put in some impermeable zones, and this is to actually simulate to capture the pressure evolution in wells that are located outside this area here. So that there is some impermeable zones and so on. And here is the extent of the stimulation zone, roughly as I showed before. And based on this, we then constructed and other data. We constructed a final model with a network of faults or fracture zones in the model to simulate this. When we then look at the evolution over longer term, you can see that okay, we have this trigger in front of induced seismicity, which is kind of driven by the pressure front, and then close to the well, you have the area where you have a lot of cooling. We actually saw there a kind of what you call a cessation front. So here you can see that there is no induced seismicity close to the well. So this is the distance from the injection wells in meters over time. So this is after 1 year. You create this zone where there is not much induced seismicity. But in this zone, we actually calculated maybe the most changes in permeability due to cooling contraction. So over time, this kind of a zone of induced seismicity actually moving down gradually into this hot rock. So that can actually create some sustainable production during this deepening. So this is still ongoing, the injection and production in this area today. So that's yes. So the next system is then the carbon sequestration. Here I'm going to talk about another interesting data set. This is from the In Salah CO2 storage project in Algeria, where you can see there's some important effect. You have the here you also have cooling, because you inject the cold CO2 that is cooler than the host rock into the reservoir. You have multi-phase flow, so a CO2 injecting into water. There are geomechanics, reservoir caprock. So caprock integrity, actually, there is also indication of fracturing in the caprock or activation of the fracture zone, which you will see later, and induced seismicity. So this is the In Salah CO2 storage project. So at that site, the In Salah gas project, which is a joint venture between BP, Statoil, and an Algerian company, they were producing gas, methane gas, and with the gas they produce some percentage of CO2, and that has to be actually separated from the methane gas before they export it. So usually the usual way is that they release that CO2 up in the air, but then they decided actually to do a kind of a carbon sequestration demonstration project and actually re-inject the CO2 into 3 injection wells in the water leg of the gas field. So you can see here, this is a plain view with a gas field. So the CO2 wells are horizontal, KB501, KB501, KB502, and KB503 here. So nearly 1 million tons of CO2 were injected into these 3 horizontal wells. And the wells are horizontal and directed perpendicular to a fracture system. So this is a fractured sandstone reservoir, but it's relatively thin and not so high permeability. So that's why they actually used the horizontal wells, about 1 to 1.5 kilometer long. So bottom hole pressure was limited to an estimated fracture gradient. Maximum pressure was about 10 megapascal, which is still quite high, 160% above the hydrostatic pressure in those wells. So one unique data set from this area is actually the ground surface deformation measured by satellite InSAR data. And these are very, very good quality data because this is in the desert, but it's hard. Actually, the surface is hard rock. So you can see it was very suitable for this kind of measurements of surface deformation. So what you can see here, you can see the surface uplift around each of the 3 injection wells. So this is about 5 millimeters per year uplift during this first 3 years of injection. You can see that this zone of uplift is extending several kilometers from each of the wells. So this would be supposedly as a result of the pressure changes induced by the CO2 injection. And so our first model of this is shown here is a layer cake model, where we include again the important units of the overburden. There was a 900-meter thick caprock above the injection zone, and then there is the 20-meter thick sandstone injection zone, and then you have the base. So we inject the CO2 into that horizontal well in the model. And using such an injection, we could actually explain the surface, the magnitude of the surface uplift we saw on the ground surface. So this is caused by the pressure changes in the reservoir, which extends much further out than the spread of the CO2. And this is then causing some uplift, about 1.6 centimeter uplift on top of the injection zone. And this is then attenuated to about 1.2 centimeter uplift on the ground surface. So these are roughly the magnitude we see in the data, and actually there was also some important impact, looks like, for pressure changes in the low permeability caprock above. Although it's low permeability, you get some pressure changes, and that also contributed to the vertical uplift. So this would indicate then that the CO2 and brine is actually confined at depth, because we could explain it by the pressure changes at depth. So this is in the first few years of injection. However, later they start to discover some kind of, when they look very detailed, they start to discover some kind of a double lobe uplift. It's maybe not so clear on this figure, but if you look in the next figure here, so this kind of a double lobe uplift is kind of illustrated here. This actually would indicate you have a kind of a tensile opening deep down into the formation. And here you can see in the red, this is this blue here is red here. So you have a double lobe uplift here. What they then did also, they did a 3D seismic contour investigation of the site. And this one shows the 3D seismic contour plot about 150 meters above the reservoir, so in the caprock. And what you can see here, there is a large zone extending about 5 kilometers long and several hundred meters wide, where you have see some changes in the 3D seismic contour. And if you overlay this one on what you see on the ground surface uplift, you can see there's this very well correlated here. So this is a huge, looks like a huge fracture zone or deep fracture or activated in this area. So the lower part of the caprock was fractured, initial fracture, but then seems that this has caused additional activation of fractures or a fracture moving up into the caprock. And the question is how far would this fracture move up, because they don't want to have a fracture moving up to the ground surface and get leakage to the ground surface. So this is something we try to analyze using the couple modeling. And here you see again, this is the same figures. So what we then did, we did the simulation where we put in such a fracture zone into the model, into the earlier model, and see what kind of surface displacement signature we can get. And here you can see the results. So if you look to the right here, you see this is a profile through the system here. And you can see the vertical uplift up to 20 millimeters here and the shape of it. So this is we simulated with the simulations and compared to the In Salah data, and that indicate that this fracture zone maybe have propagated a few hundred meters up into this 900 meter thick caprock. So that means that still there should be no CO2 leakage to the shallow groundwater aquifers. But still, because of this happening of fracturing of the caprock, actually the In Salah joint venture actually decided to actually shut down the injection into these wells, the CO2 injection. So now there is no CO2 injection going on there anymore. Okay, so these are the 3 examples I presented. And so these are kind of an examples demonstrating the use of coupled processes modeling for understanding. And I think that this is kind of, such understanding is crucial for resolving the challenges of a growing demand for surface energy storage, energy and storage we will see in the future. So I thank you for your attention. And if I can answer some questions, and if you have not, you can also send me an email later if you have some questions with this email. And there is a number of I listed a number of, I thought I listed, okay, maybe not, a number of references on this, yeah. Which you can read more details on what I presented. But I could answer some if there is any questions. No?
Thank you, Jonny. I invite the audience maybe also to thank him with an applause for this endeavor. Thanks a lot for the time in this wonderful talk. Does anybody have any questions?
Alessandro?
Yeah.
May I have one?
Yeah, absolutely.
Thank you very much, Jonny. It was an impressive set of examples, and particularly impressive the quality of the match with such complex underground systems and sophisticated constitutive models. Perhaps my question is a bit general, but I wanted to get your insight about that. So you are dealing with very complex underground systems, multiple rock types, several discontinuities, and the models are also fairly advanced. So different physics involved, different complex constitutive laws with several sources of inelasticity. What's your particular recipe to constrain the evidently large, considerable number of parameters and keep them to values that are robust, optimized? I suppose that there are multiple viable solutions for a set of parameters that may appear to work. So what's your particular recipe to constrain the calibration of the model?
For each of the examples is kind of unique in itself. So for example, for the host rock at the Yucca Mountain, it's complex, but the system, it's a highly fractured system, and we had the dual permeability model, so I think the conceptual model of the fracture system is quite simple, and then you of course they have done a lot of laboratory tests also to understand those fracture closure and the mechanical properties and so on. But actually there is also quite a level of size when you go to the field.
Yeah.
Because in the lab tests you cannot include all these big fractures. So for example, fracture permeability would be strongly underestimated if you just take a core sample and put it together, because you miss many of the big fractures and big roughness. So then I thought this kind of in situ experiments are actually very useful. So you can validate the model, and actually there are not too many parameters. So for example, for the permeability model, permeability stress model, I kind of calibrated it. This was 2 parameters, maybe to 2 or 3 parameters to get the whole thing. So if you increase the stress to very high, you get a certain residual aperture. So that's you could actually see, and also I didn't only look at this data. You also look at you have a permeability change with depth. You get to some residual aperture, and then we had other experiments where they look at the excavation of the tunnels and so on. So for that one, I'm quite confident that the permeability changes, which we kind of estimated to be roughly 1 order of magnitude, could be banded quite well, and that's maybe enough for the performance assessment in that case, because 1 order of magnitude permeability maybe is not so much actually in that sense. So yeah.
Makes sense. But
of course there could be processes that we missed or something like that.
Yeah, but it sounds that lab tests, that perhaps was my follow-up comment, are an important part of
the lab tests are very, very important to actually understand the physics. I think basic physics.
Yeah, I may have other questions, but I'll leave it to others in case there are other questions.
Thank you, Giuseppe. Yeah, so Professor Bajant, please.
Yes, a very impressive talk, Dr. Rutqvist, and also similar to some work we are doing. I have a number of little questions, but let me ask just 2. We are simulating together with Los Alamos Laboratory, the group of Viswanathan, penetration of fluid into blocks with simulated natural cracks. And this is exactly what you showed there in your pictures. That was simulated. We are doing also experiment which we could match. And we find it's very much depends on spacing and viscosity, injection rate, and one possibility is that the crack basically the penetration runs smoothly along one line. Then we get big branching, which we need for fracking, of course, branching into a big area. So I wonder what parameters are there, what was the spacing of the cracks and so forth. And my second question is more a general point. You discussed Yucca Mountain, was very interesting, but you didn't say for how long is it guaranteed. I'm not sure what the current thinking, but I remember about 6 years ago in the press reported it was guaranteed for 6,000 years. Sorry, for 1,000 years, 1,000 years, and that Congress decided, administration, that should be 10,000 years. That seemed to be somewhat crazy because in 10,000 years, who knows what happens, and we face a catastrophe environmentally in the century, right? So I don't know. So what is your view of these things?
I mean, for the last question, so the nuclear waste repository will be, they have to evaluate the safety for 10,000 years, or even some countries they do, you know, maybe 100,000 years. I mean, they have to evaluate the the performance. And yeah, I mean that's what they have to do. So, and they do. I mean, they do. I'm not doing those performance assessment modeling, but
for how long is it guaranteed that people agree?
They have to guarantee. I think the license is that they had 10,000 years. But I mean that site. Yeah, they guarantee they have to. Yeah, more or less. Yeah. So that's, I mean, that's in every country that they have this problem with it.
What will happen in 10,000 years?
Yeah. So I mean, they have to also consider future climate changes and things in the model. So they did. I mean, if there be much more precipitation and so on in the area, and changes in groundwater level and so on. So, but the Yucca Mountain site was abandoned, as you may know, because they was by some political decision, and the state of Nevada is very much against it. So it's not going to be at that site. Instead, they are now looking at the different alternatives, such as salt, shale, or crystalline rocks, but more general. There are no site decided. We are not only allowed to look at genetic studies at the moment. So they, for example, you have the waste isolation site in the plant in New Mexico, where they have the defense waste stored. So that's in salt host rock. So that's still ongoing. I mean, some other countries they are coming further, like in Sweden and Finland. They are almost starting to building a repository now that's in crystalline rock. So what the first question was about the fracture spacing in the. So I think the
spacing of the natural cracks, right?
Yeah. So like at
the spread or no spread of penetration of the injection channels.
Yeah. So I mean this is. So maybe I don't know if maybe you are working on shale gas fracturing or something.
Yes, we work on shale.
Yeah. So I mean, so maybe the In Salah example is kind of you are fracturing into a shale, or kind of a shale mudstone, and that's so that was initially that there were fractures, many fractures in the lower part of that caprock.
What is the initial spacing of the cracks?
I think it was quite. I mean, they don't know exactly, but I think it's quite densely fractured. And I think this kind of a zone where you have a 300-meter wide, we saw on the 300-meter wide and 5 kilometer long kind of fracture zone. It looks like a crack band model, I think. So
Yes.
at a very large scale. Yeah. So
Yes.
so it could be. I think it could be. You could use the crack band model to maybe analyze at a large scale, that kind of thing.
Okay, that's what they are using. Yes.
Yeah.
Thank you.
Sure.
Thank you. Are there any other questions?
Yeah, I have a questions for Dr. Rutqvist. Yeah, so I have questions about when you cover the TM and the TH processes, right? How about like the relation between the H and M hygroscopic and the thermal behaviors? Because like I have in mind, because the temperature is around 200 C, so the absorption and the thermodynamic may be shifted. And did you consider those effect of the two agents?
So you mean you have an unsaturated media with a you're talking about partially saturated media
close to saturated point.
So in the, for example, at the Yucca Mountain site, so that the fracture system was quite dry, but 10% saturated. So and then the matrix, adjacent matrix is much highly saturated, maybe 80% saturated or something initially. And then you have a much higher suction, so much higher capillary pressure function. So those capillary pressure functions has been measured in the laboratory for the, at least for the matrix. And then for the fracture, you assume something lower capillary pressure. So you're saying that the change in temperature will change the capillarity? Is that what you?
Right. So, yeah. So I guess my question is because the absorption and also like the heat of absorption may be changed due to the temperature. So the amount of suction may shift, right?
Yeah. I mean, of course, we have in the model, in the TOUGH-2 model multi-phase flow simulator, we do simulate. So when you heat the rock, you get the evaporation.
Right.
Evaporation of the liquid phase into vapor. So that will reduce the saturation due to that. So that's why you get the drying near the heat source. And then there is a vapor flow along the thermal gradient due to there is a vapor density changes. So you get the vapor flow along the thermal gradient outwards. And then when it comes out, when it's cooler, then that kind of vapor again condensate into liquid. So then you get this kind of a continuous heat pipe effect in the system. So I don't know if that's the.
Yeah. So my questions maybe lies in the parameters, like whether or not the parameters of those absorption will change with temperature. Because like 200 degrees C is closer to the supercritical point of triple junction of water, right? So
we are actually, because in this system the pressure is quite low. So I don't think we are close to this is 150 degrees or up to 200 degrees, but the pressure was very low, quite low here in this system. So I don't think we go to supercritical. Actually in the Geysers, where we go down to very deep down, we will come to supercritical fluid conditions, and actually the simulator that I used at the time could not go over 370 degrees because of that reason. But we have now other equation of state models that can do that. So it's yeah.
Thank you.
Thank you very much. So maybe I will just conclude with one question that might be interesting for everyone. Could you comment on the role of the chemistry in the nuclear waste project? I mean, I'm referring, for example, to phenomena such as elization. Were there any, do you think it is important to consider them in the modeling, or?
So that, I mean, So we have been studying elitization for the other kind of nuclear waste system where you have bentonite backfill. And then we linked that tough. Then there is a simulator called TOUGH-FLAC, and we also linked that to do THMC modeling. And looking at, I'm not the geochemist, but I have a colleague who do the reactive geochemistry on that case. And we consider the elitization and also changes. So for the looking at the what's the impact on the swelling pressure in the bentonite, because you want to have a certain swelling pressure to actually assure it's stable and tight. So the elitization, you change from a smectite to alite or something, so you can that could impact reduce the swelling stress in the system. And actually, we did some simulation, and there is some very recent papers published on that. And it was quite small effect, I think. And also we looked at the potential if you have changed the salinity of the water, you also change the swelling stress. So that's for that kind of system. Yeah, where they look at.
Okay.
I think they also looked at that somehow. The Yucca Mountain, but I don't know about elitization, but I'm not familiar what they did. And then for another chemical effect, which may have taken place like at the Yucca Mountain Drift Scale test, is that if you heat up the fractures and keep them stressed, you may get pressure solution that could close the fracture more permanently. It might have occurred, but it's difficult to distinguish from other effects if it actually occurred or not.
Well, thank you for the comprehensive explanation. So let's everybody thank Dr. Rutqvist for sharing his knowledge with us today. I think let's conclude now the seminar.